Alright, so let's ask another one of those questions. So suppose a large customer cancels an order 10% of the time, and the same customer increases their order 10% of the time. If we were to think about that in terms of a contingency table, if we put one in the columns and one in the rows, we have to think, all right, well, how many? If I have 1,000 observations, how many are going to be in the cell where a customer cancels an order and they increase their order? Well, just the nature of those two areas suggests that you can't cancel an order and increase it at the same time. And so that bin is going to be 0. Similarly, if they don't cancel and don't increase, it means that should be larger. There should be a greater count. So these two events are they're not correlated. They don't tend to be together. In fact, they're negatively correlated, and to such a degree we describe them as mutually exclusive. You can't have both. You can have one or the other or neither, but you can't have both. So that means the chance that both occur is less than 1%. It's 0%. And in the case where the chance that both occur is 0%, the chance that either occur, since the one is 10 and the other is 10, if we ask an OR question, right, will they cancel an order or increase their order, that is going to be exactly 20%, simply because there's no overlap. So if they were independent or correlated, anything other than -1, then this would be less than 20 because there would be some overlap. But there's never any overlap, and so 20% is the answer. So now that we're thinking about calculating contingency tables, and we practiced it a little bit, now the trick is going to be to take an arbitrarily stated probability problem and reverse the conditional. So here's an example of that. So if I look at this, it says suppose the probability of buying cookies assuming a milk purchase is 40%, and the probability of buying cookies assuming no milk purchase is 30%. If 60% of consumers buy milk, what is the probability of buying milk assuming the customer bought cookies? So the rationale for doing something like this is somewhat apparent from the example. So we are maybe imagining that the store might run a cookie promotion and put cookies on sale in the hopes that milk is purchased. And if that's true, we should observe a higher probability of purchasing milk when cookies are purchased. But we don't have that information. What we have is the reverse. We know how often customers buy cookies when they buy milk, and we know how often they buy cookies when they don't buy milk. So we know it backwards, but we don't know it forwards the way we want. But we do know the marginal probability of buying milk, and those three things combined will tell us what we need to know. Because at the end we can ask whether the chance of buying milk increases or decreases, or it stays the same as we add the information of buying cookies. So our step to get this to go is going to be to do an Excel calculation where we create a contingency table. And now the contingency tables we created in the past have always been given a particular number of events. But in this case, we can't do that because we don't know how many events. So what we're going to do instead is assume that these probabilities were calculated on a sample of 1,000. Now that's going to cause trouble if we try to estimate standard deviations or do some kind of confidence estimates, but in this case all we're looking for is a point estimate of the probability, and so we can maintain a convenient fiction of 1,000 observations and calculate actual occurrences in the various cells of the contingency table, which we then promptly throw away once we've backed it back out to the probability. So you'll kind of see how this goes. It sounds really wordy just explaining it, but the process is actually not too bad. So we have milk, and we have no milk. We'll put on the columns, and then we have cookies and no cookies. So this is our contingency table. We have, these are consumers who buy both. So if we have 10 people that bought both, that's where we would put that. And we don't know anything yet other than we know 1,000 people are going to be in this sample. So the column totals and the row totals are going to be 1,000. So the first information we need is the marginal probability. So that's the probability that does not contain conditioning information. That is here in this second sentence. 60% of the consumers buy milk. So if you have 1,000 consumers and 60% of that 1,000 buy milk, that means there are 0.6 times 1,000, or 600 consumers in a 1,000 consumer sample that will have purchased milk. And that also means that 400 did not. So that's great. We filled in our table a little bit, so now let's look at what's next. So we know that 40% of milk purchasers buy cookies. See how that's stated here? The probability of buying cookies assuming milk. This is the probability of buying cookies assuming milk. So we've got 600 consumers buying milk. 40% of those buy cookies. So 40% of 600, so I do 0.4 times that number, and I get 240. 240 buy cookies, and therefore 360 don't in the milk purchasing population. In the non-milk purchasing population, only 30% bought cookies, so we get 30%, and this is the difference. So we have 120 customers buying cookies, 280 customers buying milk cookies, and now we can get our row totals. So we have 360 total buying cookies and 640 total buying milk cookies. Now if you look at the situation, these percentages, it's not, you can't just tell from observation that we have 360 people purchasing cookies. If out of 1,000, 36%. You can learn these things that aren't particularly direct by inferring what they imply in a contingency table. Alright, so now that we have our table, we can ask our question: what is the probability of buying milk assuming the customer bought cookies? So if we look here, the sentence said assuming bought cookies, so we're going to narrow it down to the 360 people who bought cookies. So that's, what's the probability of buying milk assuming you bought cookies? Well, that is going to be expressed as the probability of milk assuming cookies. So we write it, and it is going to be equal to 240, because that's the number out of the 360 that actually had purchased cookies. And so we have 240 people buying both milk and cookies. We've got 360 people buying cookies, so that means 240 of the 360 bought cookies. So that's the probability of milk assuming cookies. Now we were asked what is the probability of buying milk assuming cookies, and so we get that final answer of 2/3. Now remember, the probability of buying milk is 0.6. So was receiving the additional information about cookies, a cookie purchase, relevant to the probability of milk? Yes. So it turns out purchasing cookies makes you more likely to buy milk by a small margin, and so that's an important inference that we can use cookies as a loss leader to sell milk, at least in our cute little example problem. So I have that worked out here the calculations that we did in the various cells and the final answer. So now it's time for you try it. So there is lecture 2 problems on Moodle, and go ahead and see if you can get one of those questions right. So you have to read them really carefully. There's a couple places where you can get tripped up. Specifically, you want to check and make sure that you're not getting back the original information that you put in. So if it gave you a 62% probability that a certain thing would happen, if you do a bunch of calculations and get 62% as your answer, that means that you've done something backwards. That usually means that you've divided by the wrong given information. Because at the very end, the last thing you do in any of these questions is you find the cell such that both things occurred, and then divide by the probability of we'll divide by the number of occurrences in the population of interest in the assumption, because we're calculating a conditional probability at the end. So you take the joint probability divided by the marginal for the assumption. And so if you divide by the marginal for the questioned event, you'll get your original given information back, and you'll know that you've done it wrong. And you need to divide by the other total. So if you divided by column total, you have to divide by row. And if you divided by row, you have to divide by column. So go ahead and give one of those questions a try on that lecture practice. And if that works, give maybe another one. And just if you're feeling confident, then then you'll be ready to go try to tackle these questions in the homework, which will be of similar style and format.